about previously that our sample that we're going to take should be representative of our population. So if we don't have enough data or we don't have representative enough data to represent that population, even if we get results, they may not be very reliable. So when the process is flawed, the resulting decision may be questionable. So although you may never have to develop a statistical study, it's likely you will have to interpret a statistical study. An example of this might be if you're working in a certain field, you may be getting information from some organization telling you about the newest practices or the newest findings. Or it might just be in your daily life, or you see something in a news broadcast talking about some new study or some new findings. So before interpreting the results, you should determine whether results are actually reliable. Now, when you're designing a statistical study, the first thing is you want to identify the variable or variables that is your focus, the variables that are of interest to you, and what population you want to study. So in the previous section, a lot of my examples were around USF students because that's where we are. So based on that, this might be something like if I wanted to do a study looking at the graduation rate of students who enter USF. So now I have my population, USF students, specifically USF students over a period of time, right? Those who have entered the university to see how many have gone all the way through to graduating with their degree. From that, I could then look at what variables I would be interested in. In this case, it would be graduation rate. Of those students who began at USF, how many went all the way through to graduate? And there might be other things that I need to take into account, right? How do I deal with students who transferred in after starting at USF, after a freshman year? How do I account for students who didn't leave academia or getting their degree, but maybe went to another university? Or even how do we deal with students who maybe left USF, but then maybe came back at a later date, maybe because they had some reason that they had to put a pause in their studies? So these are all things that we need to take into account when we're planning out what are our variables of interest and what population are we studying. Step 2 is then to develop a detailed plan for collecting our data. If we're using a sample, which we generally are, we want to make sure that the sample is representative of the population. Now, one thing you have to think about is when I talk about USF students, what would be a representative sample? Well, you have students who enter right out of high school. You have older students who maybe have entered later in life. Maybe they went and worked for a while. Maybe they're a veteran. You have commuting students. You have students who live on campus. You've got students between main campus, Sarasota Manatee, and St. Pete campus. You have students who are pursuing a graduate degree and those who are doing an undergraduate degree. You have non-degree seeking students. These are all students at USF. So I may have to take this into account whenever I am trying to get a sample that's representative of students at USF. Step 3 is go and actually collect the data. Now this one usually is written off pretty simply as just collect the data. But this step can actually be tremendously hard because, again, this is going to take time and resources, and you may not always have access to everybody that you want to, right? Just because you know that you want USF students, you may not have the resources to go between all the different campuses. You may not have access to all the students because some students are doing night classes, some are doing it in the morning, some students may be online only. So in the end, collecting the data might be harder than it seems by just saying, go collect the data. Step 4 is you want to then describe the data using descriptive statistics. Now, in Chapter 2, we'll talk about this central tendency and variability. These are the two most common statistics that we want to get for our data. But you might also want to describe it in other ways. You may want to make a histogram, which we'll talk about later, where it describes the shape of the data. You may want to look at trends in the data, things like that. So you'll use different methods to describe your data. Once you've done that, step 5 is to interpret the data and make decisions about the population using inferential statistics. So based on the sample that you've found or you've collected, and then once you've done your analysis and gotten your descriptive statistics, what can we infer about the population and how are we making that inference? And then last step, step 6, identify if there are any possible errors. Because no matter what, no matter how well you plan it out, there can always be errors, even if you did everything right. And the simple solution might be do a secondary study to see if it agrees with your first, or maybe collect more data So even if your sample was representative, maybe it wasn't big enough. Maybe turns out after you gathered the data that it's not as representative as you thought. So identify any errors there may be. It may not mean that your results aren't worthwhile. It might just mean that you need to be a little bit skeptical. So now let's look at types of study. A statistical study can usually be categorized as either an observational study or an experiment. So an observational study is just where a researcher does not influence the responses. So a researcher observes and measures characteristics of interest of part of the population, but does not change existing conditions. So this might be something like if you were doing a study of animals in the wild. You are not imparting any treatment on those animals. You are simply observing behaviors, you're observing rituals, things that they do, and from that you are documenting it, and then that is your study. You are observing. This also could be, for example, taking a survey. When you are using surveys, you are not imparting a treatment. You are not saying, okay, do this, and then filling out a survey. You were just walking around and saying, what are your views on this? How do you feel about that? You are observing the outcomes that already exist. An experiment, on the other hand, is where a researcher deliberately applies some treatment before observing the results. And this is what makes it an experiment, is that you as the researcher are imparting some treatment to whatever population or sample that you're looking at. In performing an experiment, a treatment is applied as part of the population called a treatment group, and the responses are observed. Now this is important because one of the ways that we can strengthen the case for whatever treatment we're using in our experimental study is that we have what's called a treatment group. This is a group that specifically gets the treatment, and we're going to observe what the outcome is. But then we'll have another group called a control group. This is a group that does not receive the treatment, but we still take the same observations to see if both groups are representative of the population. Does it seem like our treatment had any impact on whatever it is that we're observing, whether positive or negative? So another part of the population is used as a control group in which no treatment is applied. The subjects of both groups are called experimental units. And in many cases, subjects in the control group are given what's called a placebo. This is a fake treatment because you don't want them to know that they're in the control group because this could actually impact your results. If we're doing a medical study and there's a lot of belief that this could really make a big impact, well, if someone finds out that they're in the control group, this could have major implications for how they react because they know that they're not getting that treatment. And if this is possibly life-saving experimental treatment, that can have major impact. So the responses of both groups can then be compared and studied, and this will allow us to have a baseline. Our control group is our baseline where we see, okay, this is what happens when no treatment is added to the mix. The treatment group is then compared to it. Did it increase? Did it decrease? Or did it not really seem to change at all? In most cases, it's good to use the same number of subjects in each group. Now, this is not always a requirement, but if possible, you definitely want to have them be about the same size so that you can know that it's not going to be some sort of difference just because of the size of the groups. And you'll see this later on in the course when we talk about different sized groups between one thing and another. So, an example of an observational study versus an experiment. Researchers study the effects of vitamin D3 supplementation among patients who were newly diagnosed with a viral infection. To perform the study, researchers gave 2,700 U.S. adults either a daily vitamin D3 supplement or a placebo for 4 weeks. So in this case, this is an experiment, right? Because we have two groups. We have the group that's getting the treatment, the D3 supplement, and we have a group that is receiving the placebo. They believe they're getting a treatment, but they're actually not. We then observe how they react with this virus that they have, and then from there we can compare, did this D3 supplement seem to help with this viral infection? Case 2. Researchers conduct a study to determine how confident Americans are in the U.S. economy. To perform the study, researchers call 1,019 U.S. adults and ask them to rate current U.S. economic conditions and whether the U.S. economy is getting better or worse. So in this case, this would be an observational study. We are directly reaching out to the subjects of the study to determine whether they think the economy is getting better or worse, but we're not actually imparting any treatment. We did not do something with the economy and then see what their reaction was, or observe what the outcome was. All we did was say, based on how things are currently, right now, what are your views, better or worse? And then from this, it allows us to make some observations about the views of people. Okay, so now let's talk about how do we actually collect data. So first thing we're going to talk about is simulation. A simulation is the use of a mathematical or physical model to reproduce the conditions of a situation or process. Collecting data often involves the use of computers. Simulations allow us to study situations that are practical or even dangerous to create in real life, and often they save time and money. For instance, automobile manufacturers will use simulations using dummies to study the effects of crashes on humans, right? Because we're not going to put humans in a car and crash them into a wall or crash them into another car to see how well seatbelts or airbags or other safety features work. We're going to simulate it by putting in these dummies to represent humans. Same thing when testing out weaponry. They use ballistic gels to represent what the effect would be on an animal or human flesh. Another example of this might be when an architect is creating a building, they might put it into either a liquid or wind tunnel to determine the effects of like wind shear on a building. So rather than build the building and then see what happens as the wind blows on it, we can actually look at it in a simulated environment when there's no danger. Because if the building collapses, then we know that there might be some issue versus if it doesn't collapse, this might strengthen the case that this is a good design. A survey is an investigation of one or more characteristics of a population. Most often, surveys are carried out on people by asking them questions. The most common types of survey are done in interviews, on the internet, phone, or by mail. So this is different from a sample survey, which we also just commonly refer to as a survey. When we say a survey was done, we generally mean a sample survey, meaning we did something with a sample. But in this case, we're talking about taking a survey, like a questionnaire form or something like that. You've probably received them after you've gotten your car worked on, or you've probably gotten them from your doctor, things like that. So in designing a survey, it's important to word questions so they do not lead to biased results, which are not representative of the population. Now, this is where going back to that statistics is trying to accurately determine what the results are for the population using a representative sample. Survey design, this is a key aspect because you will have some people who are trying to get a certain message across, and they will word questions in a way that cause people to actually be biased towards one answer or the other, even if that's not how they feel if it were put in a neutral way. So this is something you have to be very careful about with survey questions. In fact, whenever you are taking a survey, keep that in mind. When you're reading a question, ask, is this written in a neutral way? Does this seem like they are trying to push me one way or the other? Okay, so to produce meaningful, unbiased results, experiments should be carefully designed and executed. It's important to know what steps should be taken to make sure the results of an experiment are valid. So there are three key elements of well-designed experiments. They are control, randomization, and replication. So experimental results can be ruined by a variety of factors. So the researcher must control for these influential factors. Now let's talk a little bit about each of these. Control is a factor that remains constant throughout an experiment and is used to compare the results of an experiment. This is our control group. Do we have a control so that we can then compare it to see, are we actually getting the benefits we think we are, or perhaps the negative implications we think we see? We have to have some point of comparison because let's say, for example, we looked at the happiness index of somebody in the 1800s versus now. Well, without a control, you might think, okay, well, people are happier now, but if we're not comparing them to like groups, it might be that, okay, well, yes, people weren't as happy, but what happened in the meantime? Well, we had new technologies come out. We had better health. We had a better survival rate. And it may be things that are outside of your experimental conditions. So you might say, okay, does money mean people are happier? Something like that. Well, you need to control with a group of similar individuals. You can't say people back then had less money, we have more money now, we're happier, therefore money equals happiness. It would have to be in the time frame, did people with more money experience more happiness or not? That's what you need to have, is you need to have some control, which allows you to actually determine, is the variable or variables that you're looking at or you selected actually affecting the outcome that you're measuring. The next one is randomization. It is a statistical process to randomly assign participants to groups within an experiment. Now, there's two ways we'll talk about this later on. The first one we talked about is control versus the experimental group. So when you get a sample, generally what you want to do is you want to have everybody in one big group and then use randomization to determine which group that they go into. This helps to limit bias because you're not selecting individuals for one group or the other based on any sort of reason or rhyme or reason. You're just basically saying randomize, you're going here, you're going there, and it's completely based on randomization. And this will help to limit bias because we're not picking specific people or reasons to put in one group or the other. And the last one is replication. This is a process of repeating an experiment or study to confirm the original results. Now, this is one that I think is very big. And it's actually one of the biggest problems that you've made, or the opposite, that strengthens the case of whether the results are accurate or not. It also will help us identify flaws. It can help identify and fix flaws in the original experiment. Right? So we talked about this. We talked about if I randomly select from American citizens, I might mostly get college students. So maybe I see this as a flaw and I decide I'm going to use a different sampling method to make sure that I don't have that happen again. It also can be used to apply results to other situations. So this will help us determine if the original experiment's results can be applied to different situations or populations. Maybe I have a treatment, for example. There are some drugs on the market which were originally created for another case, and they found, because of the results that they were observing, that they could be used for something else. Some examples of this would be that Botox was originally created to treat migraines, not for people to use for what they're used for. Another example is that Viagra was originally used to help treat heart conditions. Or a more recent example is Ozempic, that type of medication, semaglutide or whatever it's called, was actually originally used for treating diabetes, and it still is. But now it's also being being used to help with weight loss. So it might be that you can apply the results to a different group and see if the results still hold for that as well. And then last thing is that it can help demonstrate our results. It can help further demonstrate the original results by either supporting them, or it actually could do the opposite. It could then go against your results, showing that you might have just gotten the results by dumb luck and your results actually weren't any good. Okay, so now let's talk about variability. This is the degree of the dispersion of the data, or that is to say the spread. Is your data spread out just a little bit, or is it spread out a lot? And this can actually very highly impact how likely it is that when you take those samples that you get representative samples as much. Because if you have very spread out data, that means you're much more likely to get those results which are farther out here. If you have very tight data, it's less likely. You're probably going to be very close to that outcome that actually is there. So an example of this would be, consider these two sets of data points. You have 3, 5, and 7, and 0, 5, and 10. So if I were to take the average of each of these, the first one has an average of 7 and 3 is 10, plus 5 is 15. So take an average, you divide by 3, I get an average of 5. If I look at the second group, 0 plus 5 plus 10 also adds up to 15. I divide by 3, I also have an average of 5. So both of them have the same average outcome, 5. But if you look at that first group, it centered at 5, it only goes to the left 2 in both directions. 3 is 2 less than 5, 7 is 2 more than 5. If you look at the second set of data, 0 and 10, they're both 5 away from 5. So the second group has more variability. It varies more, it's more spread out. So next we have what are called lurking variables. So a lurking variable is a variable that has an important effect on the response variable, that is what we're measuring, and the relationship among variables in a study, but is not one of the explanatory variables, that's what we're changing, that are being studied, either because it's unknown or it's not measured. So for example, this might be something like, if I'm doing an experiment where I'm going to see how the temperature in an exam room affects students' performance on an exam. So I've got my control group, which is the normal temperature, and maybe my treatment group, I crank the temperature up so the test room is like 95 degrees. So everyone's hot, everyone's miserable, but they don't know that they're being part of an experimental condition. They just might think the AC is broken. The problem is, yes, I have a control group, I have a treatment group, but I may not know how long each of those individual students studied. Maybe my first classroom, my control group, were my early morning class where all of my go-getters were, and they all studied 10 hours for the exam. My second exam were all students who didn't really study, right? They took the late class, they don't really want to be there, they maybe studied for an hour and a half on average. So even though I have a control group, I have an experimental group, I may actually have a lurking variable, which is how much each group studied for that exam. So while one group might seem to be doing better or worse because of the temperature, it might actually be some other factor that I didn't measure. You also have confounding variables. This is when two variables are such that the effects of the response variable cannot be distinguished from the other. What this means is if I have two things that seem to closely align with each other, as this increases, the response increases, or as this one changes, the response decreases. Confounding variable is set up in a way that I don't know which one is actually causing it, right? So for example, this might be, when we talk about things like socioeconomic status, is it increase in wealth or is it increase in education that's leading to people having more success? Well, it's kind of hard to say because they both generally go together whenever we're measuring things. And the last one, we already talked about this, treatment is any specific experimental condition applied to our subjects. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.